River sharks and sawfishes are critically threatened apex predators that inhabit macrotidal rivers, waters often so sediment-heavy that visibility is measured in centimeters. In these environments, direct visual observation is restricted to the rarest of encounters. These species are diadromous, migrating across massive salinity gradients between freshwater, estuaries, and the open sea. While traditional mark recapture or acoustic tagging can offer snapshots of behavior, the physical complexity of these intersecting ecosystems often results in significant data gaps or equipment failure before a complete migratory cycle can be recorded. This lack of spatial data is most acute in the river systems of northern Australia and Papua New Guinea. These regions hold some of the last viable populations of these species, making accurate tracking a conservation priority. To understand where these animals go, researchers needed to move past external tracking and find a way to extract a geographic history directly from the biology of the animal itself. The solution lies in the fact that an elasmobranch's skeletal structure passively logs the chemistry of the water it swims through. These scatterplots show a principal component analysis of trace elements in shark vertebrae. Species cluster into distinct groups based on habitat. On the right, a tight cluster represents stenohaline species, strictly marine sharks that remain in high salinity environments. The left cluster represents euryhaline species, like sawfishes and river sharks. This significant statistical distance demonstrates that skeletal chemistry reflects their ecological lives. The primary drivers of this spread are three trace elements: barium, lithium, and strontium. We need to understand the biological mechanism that allows these three metals to serve as a permanent geographic log. To read a shark's trousal history, you have to look at its spine. Chondrichthyine vertebrae are composed of calcified cartilage that grows concentrically. Like the rings of a tree, it adds new layers outward from a central focus over the entire lifespan of the animal. Once a layer of this cartilage is deposited, it becomes metabolically inert. The shark's body does not remodel or reabsorbs the material, creating an uncorrupted chronological record of the animal's environment at the time of growth. This microscopic section shows a vertebra analyzed using laser ablation inductively coupled plasma mass spectrometry, a technique used to physically sample this timeline. A laser creates a sequence of 50 micrometer craters, spaced at intervals of 165 micrometers along a straight line from the center to the outer edge. This transect captures the animal's entire history, beginning at the focus with prenatal growth and transitioning at the birthmark into its postnatal life. Mapping time across the physical structure of the bone is the first step. The next is decoding how specific elements correspond to specific salinities. The foundation of the vertebrae is a lattice called hydroxyapatite, which is composed largely of calcium. As water passes over the shark's gills, dissolved trace elements enter the bloodstream. Because some of these elements are chemically similar to calcium, they directly substitute for it within the growing skeletal lattice. Barium is found in high concentrations in riverine environments. When a shark enters freshwater, barium locks into the hydroxyapatite lattice as a permanent indicator of low salinity. In marine environments, the chemistry changes. Lithium and strontium are abundant in high salinity water, and they aggressively substitute into the lattice, while barium uptake drops. This creates a mathematical correlation. As barium levels rise in the bone, lithium and strontium levels must fall. By measuring these metals in parts per million against the calcium baseline, researchers can generate a high-resolution map of a specimen's movements across its entire life. Applying this elemental model allows researchers to address specific unknowns, such as the reproductive habitat requirements of the endangered large-toothed sawfish. This graph plots the ratio of marine elements to barium across the boundary between prenatal growth and birth. At the exact marker for birth, the concentration of marine elements plunges. The data shows that the pregnant female, while carrying marine-heavy signatures during the prenatal phase, moved into a low-salinity riverine environment immediately before giving birth. These elemental signatures confirm that intact, accessible freshwater habitats are a biological necessity for the reproduction of this species. The sawfish's reproductive migration can be compared to the behavior of river sharks, the genus Glyphis. This timeline tracks barium ratios across the postnatal years of a river shark. The result is a flat, sustained signature of high barium from birth through year 4. Standard euryhalan sharks, like the bull shark, show a different pattern. As they age, their barium levels drop sharply, marking their migration toward high salinity marine waters. The lack of variance proves these sharks rely on prolonged, multi-year residency deep within upper estuarine environments, rather than moving to the sea. Researchers were able to generate these precise, multi-year movement models without ever tracking a live animal in the field. By translating atomic substitution into biological logs, mass spectrometry transforms inert bone into a conservation tool, providing the data needed to protect critical habitats before these apex predators disappear.